Good evening, students. Today we are going to discuss our practice paper 9. So in this paper, we have 10 MCQs, which are coming from first few theories of atomic structure lesson. And then we have several questions from chemical calculation lesson also. So this is the paper we are going to discuss today. So let's start the discussion from our first MCQ. Okay, so look at the question. Select the incorrect statement regarding the quantum atomic model. Okay, so there are 5 statements. You have to select the incorrect one. Okay, so we have to quickly refresh our knowledge regarding these quantum numbers, right? So there are 4 quantum numbers which are used to explain the behavior of electrons in quantum according to quantum theory. Okay, so those 4 quantum numbers are principal quantum number, then we have azimuthal quantum number, then we have magnetic quantum number, then finally we have spin quantum number. So those 4 are the quantum numbers, right? And for them we have these symbols N, L, ML and MS. Okay, principal quantum number, azimuthal quantum number L, and magnetic quantum number, spin quantum number. Okay, those are the 4 quantum numbers, and by each quantum number something specific is represented. Okay, so from our first quantum number, main energy level is represented by that. So we know that electrons are existing in energy levels. Okay, so those energy levels are represented by this. So this can have numbers from 1 to infinity. Okay, then the second quantum number is representing we say sub energy level. Okay, so in our main energy levels are subdivided. No? Okay, those are divided into sub energy levels. So for example, first energy level has 1 sub energy level, and the second energy level has 2 sub energy levels, like that. So energy levels are again subdivided. Okay, so like that, those sub energy levels are represented by this. So here then n can have values from 1, 2, 3, like that, and then this L value can be like this. Okay, so we have a sub energy level, P, D, like that. We have sub energy levels. For them, our L values will be 0, 1, 2, like that. For F sub energy level, we use the number 3. And there is a reason behind selecting this 0, 1, 2, 3. Okay, because when we go to the next quantum number, we are representing orbitals. Okay, so there is a fixed number of orbitals then that can each sub energy level can contain. Okay, so for example, S sub energy level, there is 1 orbital, and for P sub energy level there are 3 orbitals, and for D we have 5 orbitals. Okay, remember, like that, this will have 7 orbitals. To represent them, we use this magnetic quantum number. So in that case, we represent them by stating the value of mLs will be from minus L to plus L. So here the magnetic quantum number for the S sub energy level will be 0, and for this one minus 1, 0 and plus 1. Can you now understand why did we selected this one? Okay, because we can easily label them from minus 1 to plus 1, isn't it? We can give 3 numbers, that's why we selected that. So likewise, we can remind what is it's from minus 2, minus 1, 0, plus 1 and plus 2. So like that, actually these electrons are existing according to quantum atomic model in these orbitals. Okay, in these orbitals. So for example, S orbital will be spherical shaped one, and P orbitals will be dumbbell shaped perpendicular ones. Okay, and then for D orbitals also they will have a certain shape. Okay, like that we can understand. What is the last quantum number? It is actually representing the spin of electrons. So in each orbital we can occupy maximum up to 2 electrons, and those 2 electrons will be spinning to the opposite directions, clockwise and counterclockwise. So likewise we can fill electrons in this way. Okay, now look at the first statement. Magnetic quantum number ml represents the orbitals magnetic quantum number ml represents the orbitals. That is actually true. Okay, so it is representing the orbitals in a given sub-energy level. Understand? Given sub-energy level. Okay, but in addition to this one, remember in our theory tube, we had some other idea also. For example, main energy level or our principal quantum number mainly representing the energy. Okay, so it's representing energy of the electrons. Okay, and then our second quantum number, in addition to representing the sub-energy level, it is representing the shape of orbital also. Shape of orbital also, right? So depending on the value you choose for L, the shape of the orbital is going to change. Like I said earlier, S is going to be a spherical one, P is going to be dumbbell shaped ones, like that. And then our magnetic quantum number is representing the orbital orientation. Orbital orientation. So like that, there are some additional ideas also regarding the electron, regarding the quantum numbers. Understood, Lamai? So those are the things we have to know. We have to just, if I say quickly something, this is what I have to say regarding these quantum numbers. Okay. Now, according to the things we refreshed, the first statement is correct. Understood? So some of you had selected, only a few kids selected this also, but now I think your doubts are solved. Okay, right. Now look at the second statement. Okay, look at the second statement. Second statement tells if the principal quantum number is n, okay, the total number of electrons exist in the given energy level is n square. So it is telling you the total number of electrons is going to be n square. So that is wrong. Then tell me what will represent the total number of electrons. If it is not n square, then what it should be? Okay, can you send that one to the chat, Raman? Okay, very good. It is going to be 2n square. Okay, so if let's say principal quantum number n, principal quantum number is n. Okay, we have n number of sub-energy levels. Okay, and then we have n square of orbitals. Okay, then we will have 2n square of electrons in that energy level. Remember that one, huh? For example, if now we can write an example here. If n is equal to 3, right? So there are 3 sub-energy levels. So what are those 3 sub-energy levels? S, P, and D. Okay, you can say 3S, 3P, and 3D. And if n is 3, there will be n square of orbitals. N square. That means 3 square is, there will be 9 orbitals. That is true, no? You can see here. S, there's 1 orbital, P, there are 3 orbitals, and D, there will be 5 orbitals. You add them up, then it will give you 9 orbitals. And there will be 2 times 3 square number of electrons. That means 18 total electrons. That is also true. You can understand in third energy level, there are 18 electrons. So if value is n, this is how n will represent other variables. Okay, so there will be n number of sub-energy levels, there will be n square of orbitals, and there will be 2n square of total electrons. So remember that one. Understood, Lamai? There is something important to remember. So it's not, the second statement is the wrong one. It is not n square, it must be 2n square. So you always have to go for the obvious answer. Okay, so you can see first one is true and second one is going to be the wrong one. Okay, so any doubts regarding that one? It's not that difficult even, but still you can ask for the doubts. Okay, right? So let's go to the third statement and see what is this third statement telling. If the value of n is 4, the value for L are from 0 to 3. Yeah, that is also true. That is also true. if the value of n is, that means if it is fourth energy level, the value of L is going to be 0 to 3. That is true. Like I said here, it's going to be true. I write something here. So if it is n equal 4, there will be 4s, 4p, 4d, and 4f. There will be 4 sub-energy levels. Okay, there will be 4 sub-energy levels. So these are represented by 0, 1, 2, and 3. So that statement is correct. Okay, if the value of n is 4, then there will be 0 to 3 number of what do we call value for azimuthal quantum number. Okay, so third one is true. Like that, we will see why fourth one is correct. The value of principal quantum number n may be a positive integer from 1 to infinity, like I said here. That is true. Fourth statement is true. Then you can go to the fifth statement. When L is equal to 2, sub-energy level is D. Yes, that is true. See, it is D sub-energy level. So fifth one is also true. So what you have to write for the review, okay, get this small kind of the short note I gave you, and just write it as it is there in the board, and then add your own points also, and say why the second one is wrong. Okay, then you can express these two the things you can remember, and then complete the review by telling others are true because of this reason, like that. Yeah, now let's go to the second MCQ. So the number of electrons associated with the quantum number n equal 3 and ml minus 1, n equal 3 and ml minus 1. So I'm going to use the same chart in the board, same explanation in the board to explain the answer for the second one. From the students who answered, majority of you got the correct answer for the second one. Correct option is going to be answer 2. But however, some of you had selected other answers. I mean answer 4 also. Let's see why those things are not going to be our answer. And let's see why the second one is going to be our answer. Okay, right. So the number of electrons associated with the quantum number n equal 3 and ml minus 1, ml. Okay, so ml is coming for the azimuth, this is called magnetic quantum number. Okay, so then if you take this representation here, so it is going to show you what are the ml values that can come. Okay, because ml values are representing these orbitals. Understood? And then you can see ml minus 1, okay, can be found only here and here, isn't it? So third energy level will have 3s, 3p, and 3d only, no? So that means only these will be there in third energy level. Okay, so there you have minus 1 for one orbital will be there in 3p, and there will be one orbital in 3d also. Okay, so for the second MCQ, you can write a small statement like this for the second MCQ. N equal 3, that means third main energy level. So in third main energy level, we have 3s, 3p, and 3d. So in you can say this one will contain 1 minus 1 orbital, and this d will also contain another minus 1 orbital. Okay, so you can give it as a statement. You can say only 3p and 3d sub-energy levels will contain one orbital with ml minus 1. Okay, so that's the explanation. You can draw this also to explain. Is that clear, Lamai? So how many electrons will be there? Only 4 electrons in those two orbitals, right? So take that one clearly And do you have any doubt regarding that one? So I hope it is totally fine. But still, if you are having any problems, please ask. Okay, so what we are going to discuss in this week is regarding the electronic configuration. Okay, so after learning, we talked a little bit regarding electronic configuration also in our last theory class. But once we fully fully understand regarding the electronic configuration, there are some points I have to teach you. So after that, we can do some the next level MCQs. That means there can be questions in the exam that you need the knowledge regarding both quantum numbers and electronic configuration. Okay, so in our this week class, we will be trying some questions in the class also. But in our next week theory class, okay, here we're going to discuss another set of questions also, right? So that is the improved version of this question, right? Because here these two questions are just asking regarding the quantum numbers only, right? But if you add the theories of electronic configuration to this one, then it will be a little bit improved version. Okay, I'm not telling they are hard, they can be done, but just learn the theories properly and then practice. That's it. Okay, so practice is the secret behind everything. Okay, now by now you may have realized that one, because we have done like several papers until now. So you can see yourself is improving, right? So what you have to do is continue this thing. Okay, so those who missed the earlier classes, okay, so at least start now. Okay, you can start the discussion, writing the discussion from this paper. Okay, then start from here and then continue. Okay, when the time allows, you can try and write reviews for the earlier papers also, but start now. Okay, right. So let's go to the third MCQ. There are 5 statements in this third MCQ. So you have to select the correct statement. That means 4 of them will be wrong, right? So the third question, first statement, so it is telling like this: the de Broglie wavelength associated with H2 molecule is shorter than the de Broglie wavelength of neon atom traveling at the same speed. So it's asking about the de Broglie wavelength. Remember, we before, even in the last week paper also, we discussed regarding the de Broglie wavelength. It is lambda equal h over mv. Okay, lambda is the de Broglie wavelength. Okay, so de Broglie wavelength, basically it is telling that it is giving you the wavelength of any particle. Okay, so according to Einstein, waves are behaving like particles. Okay, and using the same theories, de Broglie argued that particles also should behave as waves. Okay, so as a result, he derived this formula, and then he showed that any particle should have this wavelength given by this formula. Okay, right. So anyway, when it is traveling at the same speed, that means this one is constant, and h is also anyway a constant. No? Therefore, we can say lambda is inversely proportional to the mass. Okay, so then if you take the two molecules, hydrogen molecule and neon atom. Okay, so hydrogen molecule will have a relative atomic mass of 2. Okay, so neon will be having somewhere around 20 something. Okay, so you can see now neon is heavier. That is a heavy atom. Okay, so then when what it is telling is H2 molecule will have a shorter de Broglie wavelength. Say if the mass is lower, then de Broglie wavelength is going to be higher, isn't it? So H2 will have a higher de Broglie wavelength than the neon atom. Okay, so therefore our first statement is wrong. Understood that? First one is going to be wrong. So like that, when you are reviewing, just show why you are coming to that conclusion. Okay, so give a clear explanation as much as possible. Right. Now look at the second statement. The de Broglie wavelength associated with a helium atom traveling at the speed, this value they give 2 into 10 to the power 5, and longer than the de Broglie wavelength with another helium atom. So traveling at the different speed. So it is the same atom, but it is having two different speeds. So like that, again, we can take H over mv formula. Now the Planck constant and the masses are the same, right? So therefore we can say lambda is inversely proportional to the velocity. So when it is traveling at a, let's say, higher velocity, then its de Broglie wavelength is going to be lower. So, but the question is telling the helium atom travels at 2 into 10 to the power 5 will have a longer wavelength. So it is wrong. Okay. So if the speed is higher, then its wavelength is going to be lower. Understood? So helium atom with the higher speed will have a lower wavelength. Okay. So therefore, second one is wrong. Right? And then you can go to the third one. So they are asking for the correct option. That means 4 statements are incorrect. Now look at the fourth one. The energy of a photon associated with infrared waves is larger than that of X-rays. Okay, so photons energy, okay, is higher for X-rays. No, it is not for infrared waves. Infrared waves will have a lower energy. They have a lower energy even than visible light, isn't it? So here's the theory. Energy is given by the Planck equation. So let's say if it is having a higher frequency, it will have a higher energy. So frequency of X-rays are higher than the frequency of infrared radiation. Okay, so therefore photons of X-rays should have a higher energy. Okay, so like that, this is also wrong, right? And let's go to the fourth one. The fractions of photons can be absorbed or released during energy exchanging processes. So no, that's never going to happen. No. So how do we say that much certainly? Because we have this Planck theory, okay, Planck's quantum theory for waves. So it says basically 3 things. Okay, so what are the 3 things said by Planck's quantum theory? So the first one is, remember, energy is quantized. Energy is quantized. That means energy is divided into small energy packets. He called them as quanta, but later Einstein called them as photons. Okay, and then he said a way to find energy of one photon equal h nu, or you can replace this one with c over lambda. Okay, energy of one photon. And third, but the most important thing, he said that none of the processes is going to absorb or release fractions. Always energy absorbing and releasing, energy absorbing and releasing occur in whole number multiples of, okay, no fractions can be absorbed or released. Understood that? So therefore our fourth statement is wrong according to what this is? Planck's quantum theory. Okay, according to Planck's quantum theory, this one is wrong. And then our fifth statement must be correct, no? So now let's see what is the fifth statement. So this theory point, it wasn't there in our early paper discussions or theory discussions. So therefore you have to highlight this fifth statement, okay? So what this fifth statement is telling? Photons that are having same frequency may have different wavelengths. Okay, so that's something very important. Photons that have the same frequency may have different wavelengths. Okay, so I'm going to explain this one and you can understand. So c equal nu lambda. C is what? The speed of the wave. Okay, usually this one is used as a constant. So therefore, I will use it as the velocity, or you can say speed. Speed is equal to frequency times lambda. So if it is having the same frequency, okay, so you know that if it is having certain energy pattern, then its frequency should be constant. Okay, so let's say red color will always have the same frequency. Understand? So if the frequency is constant, then your speed of the wave will be proportional to the wavelength. Okay, so here's why it is going to be important. Okay, have you heard about these electromagnetic radiations? They travel at the speed of light. That means 3 into 10 to the power 8 only in a vacuum. So when electromagnetic waves are traveling in other media, let's say through air or through glass or through something else, let's say through water, so it will take a different speed. Speed is going to be changed. So as a result, when speed is changing, what should be changed then? You can't change the frequency now. So what is going to be changed? When speed is changing, wavelength is going to be changed. Okay, so this is the reason for bending of light rays when it is passing from one medium to another. Remember, we call it as refraction. Okay, remember that part. Okay, so as a result, due to the different speeds of photons, they are going to get refracted. Okay, so let's write that one. Refraction occur as a result of having different speeds in different media. Okay, so when the speed is changing, wavelength is going to get changed. So this statement is actually correct. Okay, Lama, understood that one. Okay, photons that have same frequency, right, and they can have different wavelength, because when they are refracting, they will have different wavelength. So fifth one is our answer. Fifth one is the correct option. So you can write additional one here. During refraction, lambda is changing, frequency is constant. Okay, frequency is constant because energy of photon is constant. Energy of photon is constant. It should be constant. No, you can't change the photon's energy. What you can change is the wavelength of that, right? Okay, so now let's go to the fourth question. It is again asking us to use the Planck's equation. Okay, wavelength of a microwave is 1.5 centimeters. A microwave oven produces heat at the rate of 12 joules per second. If 1 minute is required to heat a particular food item, number of photons released from the oven is. Okay, so it is telling us several data. So in fourth question, there is a microwave, and that microwave will have a wavelength of 1.5 centimeters. Okay, 1.5 centimeters, and it says this oven is producing energy at 12 joules per second rate. Okay, 12 joules per second rate. So and it says it operates for 1 minute. Operates for 1 minute. 1 minute means 60 seconds, no? Okay, so it's asking how many photons are released. Okay, let's see how to do that one, right? So from the wavelength, what you can find? From the wavelength, we can find energy of one photon, isn't it? Because energy of photon is given by equal hc over lambda. Remember this formula. Okay, by applying this, we can find the energy of one photon. Okay, energy of one photon. Right, and then what is this data? So joules per second. Remember, what do we call this one? Joules per second. In all levels, you learn this one. Huh? What is joules per second? It is power. Power. Okay, so power is what? The work or energy is divided by the time. So the rate of doing work, that's how we call it, no? Rate of doing work. So if you want the energy, then, or you can say total energy, what we have to do, simply multiply the power by time. And we know the power, and we know the time also. So from using these two data, we can find the total energy. We did a similar question in last week or the before one, no? Remember? There's a similar question. So total energy can be found in this way. So power into time. Okay. So now what they're asking is number of photons. So now you know energy of one photon, and then you know total energy also. So how do we find the number of photons? It's very simple. You have to divide the total energy by the number of photons. Okay, you have to divide the total energy by energy of one photon. Okay, energy of one photon. So number of photons will be, you have divide E total by energy of one photon. So what is the E total? PT. Then you have divided by Hc over lambda, which means after simplifying, it's going to be number of photons is equal to Pt lambda over H into C. Now you can substitute values for this and see the answer. So power 12 joules per second. I'm going to use this space. 12 joules per second. And time, it is 60 seconds. And then lambda is 1.5 centimeters. So 1.5 centimeters means 1.5 into 10 to the power minus 2 meters. That is also important. Converting centimeters into meters, you have to multiply it by 10 to the power minus 2. Okay. Multiplying by 10 to the power minus 2 means dividing from 1000. Okay. And then H 6.626 into 10 to the power minus 34 joule seconds. And C is the speed of light, 3 into 10 to the power 8 meters per second. Now look at the data. So each unit is going to get cancelled. No? Here joule to joule, per second to second, and second to per second, meters to meters, they all get cancelled because it should be, because number of photons will not have any unit. No? So then all the units here must be cancelled. Understood that? So then you will get the answer from here. Okay. So we're going to simplify the numbers separately and then the 10 to the power separately. Okay. So 12 into 6 into 15 division 6, let's say 6.6, okay, into 3, right? Then you have 10 to the powers. Here 10 to the power minus 26, and up here you will have 10 to the power minus 2. Okay, and here you can cut this one with 6. It's going to be 1.1, and then you can cut this one with 3 also. It's going to be 4. So 4 times 15, it is 60. And then you have 1.1 and 10 to the power minus, so 10 to the power 24. 10 to the power 24. Then if you put this one together, it's going to be 6 over 1.1 and 10 to the power 25. So there's only one answer which meets this possibility. Okay, so if you divide this one by 1.1, should be something lesser than 6. Something should be 5 point something. Okay, and the power of 10 will be 10 to the power 25. There's only one answer given that. So what is that? The second option. Okay, so answer is going to be answer 2. Okay, so let's see what is the question number 5. It's about subatomic particles. So neutrons can be found in all the atomic nuclei. So will you found neutrons in all nuclei? And we found neutrons. So it is wrong. So you might remember this one from our very early discussions. We talk about this. So there is one atomic nuclei that doesn't have any neutrons. Tell me what is that? Can you send a message? Yes. What is that nucleus without any, and very good. Okay, Ashima. So it is protein. Yes. Okay. Good. 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 Yeah. Some of you are telling the correct answer. Protein doesn't have any, neutron. Protein. So in our question 5, the first one is wrong because protein does not have any neutron. Any neutron. So if you take hydrogen's isotopes, H11 is the protium, then you have H12 deuterium, H13 tritium. You might remember this graph. If you take protons, there will be 1. And if you take electrons, that also will be 1. Okay. But when you go to the neutrons, here you will not have any neutron because mass number is 1. So that means there will be no neutrons. Here 1 and 2. So that's why we say the first statement is wrong. Okay, good. And then we can go to the second one. The deflection of alpha particles in electrical field is greater. So that is wrong. Deflection of alpha particles will be smaller. So why alpha particles show a smaller angle of deflection? Okay, you can say angle of deflection for alpha is small due to its higher mass. Its higher mass. So, but in the other hand, our beta particle, which is equivalent to electrons, will show a large deflection angle. Remember our diagrams? Okay, you can turn your book and see the images, right? So, second one is wrong. Then let's see the third one. Compared to the mass of proton, the mass of an electron is approximately 1/1840. So that one is anyway correct. Okay, because if you take the mass of proton as 1, then electron is very, very lighter particle. So it will be 1/1840. Okay, so you can write some additional point to this one. Mass of proton is nearly equal to mass of neutron, but mass of neutron is little bit heavier, slightly heavy. That point also can be asked right there. Then our fourth and fifth statements also should be wrong. So what is the problem with the fourth statement? Alpha particles may be considered as similar to helium atom. It's wrong. So then what we can consider it to be similar? If it is not helium atom, so what is alpha particles? Tell me, Lama. Alpha particles are, we can consider them to be equal to helium. Yes, nuclei, not atom. Okay, very good. I'm having several answers. Good. It is helium 2 plus. So alpha particles equivalent to helium nuclei. Or you can say helium 2 plus. See how they're asking? Now look at the last statement. All particles obtained in positive ray experiments are protons. All particles. So it is wrong. Why it is wrong? Should be wrong. Why? Okay. Protons is H plus. Proton is H plus. You will have H plus only when hydrogen gas is used. Okay. Okay, you can write in positive ray experiments, H plus is given only when hydrogen gas is used. For other gases, other positive particles will be given. For example, earlier in theories we discussed, if you use nitrogen gas, N2 gas, you will be having N plus or N2 plus, something like that. It's not protons. And remember, proton is basically it's same as the hydrogen plus, okay? Because when you take this H plus protium, you remove the single electron, you will have only the proton, right? Understood that? Okay, so you have to assume that we are talking about only the protium. Otherwise, again, we might get confused because hydrogen may contain other isotopes also, but mainly hydrogen will contain protium isotope majority. Remember, even though there are 3 isotopes, you can't find them equally, no? So this first one is more abundant. Okay, so basically when they ask questions like this, you have to think about that abundant isotope. Right, so it's a good question anyway, not that difficult, however. Answer 3 is there. So nothing much to talk about answer 3, but we can talk about why others are wrong. That's why I selected that question. Okay, now let's go to the chemical calculation question. Ammonia can be synthesized at high temperature according to the following unbalanced equation. So they have given us an equation, and it is telling in an industrial manufacture 17 grams of ammonia was produced using 45 grams of NO and 12 grams of H2. Okay, 12 grams of H2. So it's asking the limiting reagent and the percentage yield. Okay, so first of all, let's balance this one. NO gas is reacting with H2 gas to form NH3 gas and H2O gas. So they all are in gaseous state. So to balance this one, we are using inspection method. Remember, we check the 2 sides and we put some numbers. It's until the 2 sides are having same number of atoms. Okay. So in front of this, now if you check just check superficially, you can see 1 nitrogen is there. Here also you have 1 nitrogen. 1 oxygen is there. In this side also you have 1 oxygen. So the problem is with hydrogen. Here in the right side you have 5 hydrogen atoms, but in the left side you have only 2. So therefore, when you want to balance it, you can write 5 by 2. Okay, but we can't put fractions here. No? So therefore, what we do, we multiply the whole thing by 2. Okay, so then it will be 2, 5, and 2, and 2. Now let's check again. In the left side, you will have 10 hydrogen. In the right side, you will have 10 hydrogen. No problem with that. Okay, so now this is balanced. And it says that they get 17 grams of yield, and they have added 45 grams of NO and 12 grams of H2. 12 grams of H2. Now, here we are following added reacted remaining method. I hope you remember that one. So, in each paper, I gave one question at least because it's so good to revise again and again and again. That's why. Okay, so here we are doing another question today, right? Right. So first of all, in this method, we need to find the moles. So let's get the moles of NO. 45 grams divided by the NO molar mass is 30. Okay, 30 because 14 plus 16. 30 grams per mole. So you'll have 1.5 moles. Then we can get the moles of hydrogen. You have to divide this 12 gram by 2 grams per mole. Okay, so then it will be 6 moles. 6 moles. And here you have 1.5 moles. Here you have 6 moles added. And then what is the limiting reactant? What is going to fully react? Okay, so by now we have a good practice. Okay, so if you reacted this, if this whole 1.5 reacted, you will be you can get this value by simply doing this. Okay, you can divide this 1.5 by the given stoichiometry, and we can multiply it by the required stoichiometry, divided by 2 and multiplied by 5. So that means 0.75 is the answer that you get if you divide it. Then you have to multiply that one by 5. 0.75 by 5 So 25, 30, 3.75. Okay, so you will be needing 3.75 of this one. So, but you have more than that, no? So there's no problem with that. Your NO is going to fully react. Okay, and here if 2 reacted, 2 will be formed. That means if 1.5 reacted, 1.5 will be formed. 1.5 will be formed. So this is actually Lamai, we expect this value. Okay, we expect this value. So then remaining, there's nothing remaining here. Nothing remaining here. And here some amount, that means 2.25 will be remaining, and here 1.5 will be expected, and 1.5 will be expected. Okay, so this is how what is coming after completing the chart. Okay, you can think, okay, if you want to react this 6 moles fully, how many moles of NO you need? You can divide this one by 5, then it comes 1.2, then multiply it 1 by 2. So you need 2.4 grams of 2.4 moles of NO. So you don't have that much of NO, isn't it? So therefore, this H2 will not fully consume. It will remain. Okay. So here you can say NO is the limiting reactant. So you can cut all the answers that are starting with H2. So there are 2 answers you can remove. And what is this percentage yield? Percentage yield. Here I said we are expecting 1.5, no? So percentage yield is something like this. It's something like you are answering to a test paper. Okay, so in test paper, the examiner is expecting 100 marks from you. Okay, so this is our expected yield. But let's say student is getting let's say if there are 20 questions, student is getting 15 questions right. So that is the actual result, actual yield. Okay, so here we are putting actual yield. And then we are going to state it as a fraction, then as a percentage. Okay, so your actual yield will be 17 grams. Okay, and your expected yield is going to be 1.5 moles into 17 grams per mole. Why? It's the molar mass of ammonia. And then you can put it into 100%. You can now see 17 and 17 get cancelled. Okay, so you can divide this further. 200 division 3, which means 66.67%. This is your answer. Okay, so is that clear, Laman? So I saw most of you had done it correctly. Very good. What about the 7th question? 7th question also majority of you had selected the correct answer. Yeah. Let's see the 7th one. That is also a good question. Again, another calculation. When carbon monoxide is passed over Fe2O3 under hot conditions, a portion of Fe2O3 first converted to Fe3O4. So they are telling some story, okay? When you pass some carbon monoxide, it says first it is converting to Fe3O4. Then when you continue to pass carbon monoxide, it is going to convert it to FeO. That's what they are telling. So basically, you can skip this Fe3O4. What's the purpose of having that? No? You can just skip that one. So you can say directly, when you use carbon monoxide excess, it is going to get into carbon FeO. Sorry, Fe2O3 will go to FeO. So when you are balancing this also, you have to balance using the first and last compounds. So ignore this Fe3O4. According to the question, you can see it is not needed. That's why. So then Fe2O3 with CO going to form FeO and CO2. It says it forms CO2. And then there are 2 Fe's now. So if you use the inspection method, you have to put 2 in front of FeO. And now you can see this is balanced also. This is balanced also. right? And so not all the Fe2O3 is converting. So some Fe2O3 will be there without having any conversion. So this is the initial amount. You will have 16.0 grams, and this is the final mixture. It is 15.6 grams, okay, which is containing FeO and Fe2O3. So there are several methods you can do this one. Let's say out of the total moles, you can find the total moles by this. This is a pure sample of FeO, Fe2O3. So we can find moles of Fe2O3, which is 16 grams division 160 grams per mole. That is the molar mass of Fe2O3. You will have 0.1 mole. Okay, so this is 0.1 mole. Let's say from that X amount is decomposed. Then you will be having 2x moles of this one. So some of you got a different answer because of not considering this. Okay. And here 0.1 minus x will be there without undergoing any change. Okay, without undergoing any change. Now we can use this value, no? Isn't it? So if you consider this sample, we can say mass of FeO and mass of the remaining Fe2O3 is equal to 15.6. So you can multiply these moles by molar mass of that one. FeO molar mass is given 72. So 2x times 72 is the gram, and 0.1 minus x times 160 is equal to 15.6. Now if you simplify this, you can get the value for the x. Okay, so 144x plus 16 minus 160 is equal to 15.6. So if you just simplify this further, this side will be 16. It's equal to 0.4. 16x is equal, no, 16 is equal to, where's this x again? This 160. Yeah, 16x is equal to 0.4. 0.4. That means x is equal to, okay, 0.4 division 16, which is 0.1 division 4, 0.025. So this is the moles of Fe2O3 decomposed, because I selected that as x moles decomposed. Okay, so now I got the answer in moles, but they are not expecting the answer in moles, no? They are expecting the answer as a percentage, mass percentage of decomposed Fe2O3. So how do we show that one? Decomposed percentage is equal to, you can multiply this one, 0.025 into 160, that's the decomposed mass, and 16 is the initial gram, and then put it as a percentage. Okay, now you can see this easily simplifying, and it's 25% is decomposed. Okay, so some of you got 50% because of that ignoring this 2x here, right? I hope you understand that one. That is also a somewhat good question. So we are looking at here balancing and inspection method for balancing, and what do we call this one, stoichiometry related question. Then you can do the same question using the mass difference also. Okay, I'll write that too. You write that as an alternative method. So what is the mass difference here? Mass difference is 16 minus 15.6. You will have a 0.4 gram mass difference. That mass difference is due to oxygen. Okay, so therefore we can find moles of oxygen atoms. because you can see one oxygen from here is taken to the carbon dioxide, taken to form carbon dioxide. Moles of oxygen will be 0.4 division 16, which is 0.025 moles. So then you will have equal number of moles. Now let's say if one oxygen is removing, that means one Fe2O3 is decomposed. Okay, so you can write that one here. For one oxygen atom lost, one oxygen mole lost, 1 mole of Fe2O3 is reacted. Like that you can say. Therefore, reacted Fe2O3 will be, again you can find the same answer. Understood that one? Therefore, reacted Fe2O3 is equal to 0.025 moles. Okay, Lama? So that's a good question. Huh? That's another method. You can try the same question. You choosing the mass difference. Usually, I prefer that method. But anyway, I thought of showing you the, molar mass and other method, because that is the method most of the students are approaching. But you can try this. It is really easy. Okay. Right. So any questions on the 7th one? So we have a few more questions to discuss. So question number 8. This is somewhat a different question. So some students ask about this question also when I gave you the paper. So why it is different? Why it is different? So it is because, Lamai, it is showing you the wavelength. Normally we are used to draw emission spectrum in terms of frequency or energy. But now it is giving you the question in what? In wavelength. So when you increase the wavelength, what will happen to the energy? Energy should decrease, no? So I'm going to copy that emission spectrum in the board. Okay, so the series X is having a line called A here. It will have longer gaps to the series X. And then you have the B line. This is the series Y. And then you have the C series with shorter lines. And this is your C. And this is the series Z. And from left to right, wavelength increases. So wavelength increases. So finding the answer is not that difficult and manage. So here you have wavelength increases towards the right side. Okay, which means this series is having low energy, and the series to the left side will have the higher energy. So normally we used to see higher energy ones are having bigger gaps. Why? Because we draw earlier according to the energy. That's why. Okay, but now we are drawing this one according to what? Wavelength. That's why the high energy series will have very close lines. Okay, so that means you can be given a similar one in your exams also. Okay, have to think. So if the wavelength is increasing in this way, let's say energy increases in the other way. Say this is the energy increasing direction. Then your lines will have a bigger gaps in this side. And this is going to be your series Z. Going to be the series Y. And series X is going to have very small gaps. This is what we used to see, no? And we call this one as Lyman series, remember? Lyman series, and this is as the Balmer series. And Paschen series, this is what is familiar for us. Now what I'm showing you here, it can come in this way also. Okay. And this is going to be our Paschen series, low energy Paschen series. And this is going to be the Lyman series. And this is our Balmer series. Finding Balmer is no problem. So you can go to our tute page number 14. There you have wavelengths. So I'm going to copy some wavelengths in this diagram just to make sure you understand it properly. And in Lyman series, these lines, and this is going to be 122 nanometers. Okay, and the next one 103 nanometers, and the before that one you have 97 nanometers. So they are having small nanometer values, but when you take the Paschen series, Paschen first line is 1875 and the second line 1282. So they have hundreds of gap, a very big gap. Okay, and this one is having 1094 wavelength. Okay, so gap likewise, Paschen series are having small energy gaps, therefore large frequency gaps, large wavelength gaps. Okay, so you can write that also. Paschen series, between lines there are small energy gaps, therefore wavelength gap, lambda gap, will be larger. So now you can relate the first this diagram and the one we used to draw earlier. Okay, so remember this one, put a star, and I recommend you to add this one to our note also. Okay, because yeah, it can be there in your school term test, and actually I got this question from a school term test paper. Okay, right, now let's check the other statements. Emission spectral lines ABC occur when the electron transitions. So now since we understand this, A is the Paschen series. Now Paschen first line is from 4 to 3. Balmer first line is from 3 to 2, and this is 2 to 1. So that's correct. And these series are in this way. Second one is also correct. Third one is also correct. Right? And the range of wavelengths of Z series reduces due to having high energy frequencies for them. Yeah, that's why we have lesser gaps here. The opposite of the sentence I wrote here. Understand? And then the line B, which is in the series Y, appear to be green color. So a lot of students selected that one. That's correct. So what is actually the color if it is not green? Yeah, what is the color then? The line B, it's not green. You know, Balmer's first line is what? It is going to be red. Red. That is the reason. Okay. And then last statement, X, that means Paschen series belongs to the infrared region. That is also correct. Yeah, why there are 5? One of you are asking why there are 5 lines in the tute belonging to the Y series. Y series means what? Y is Balmer series. Balmer series, how many? 5 lines? In the question here. Yeah, it can have Lamai. Okay, only 4 lines are visible in the Balmer series. Okay, but Balmer series can have more than 4 lines. Okay. Okay, only 4 are visible, others will be there in UV region. Is that clear? Okay. You can have as much as lines you want because there are infinite energy levels. No? But in Balmer series, only 4 of them are visible. So it's a good question. No? Put a star and study that question also. What about the question number 9? The incorrect statement regarding the atomic spectrum of hydrogen. So let's see that one. The line represented by H beta correspond to the transition from 4 to 2. That one is correct. 4 to 2 transition is. So these are the energy levels. So let's say this is n equal 1, 2, 3, 4, and yeah, n equal 5. And then I want 6 also for this discussion. N equal 6. And there may be infinite energy level also with some energy. Okay. And the line represented by H beta corresponds to the transition from 4 to 2. 4 to 2. This one. Okay. So the in Balmer series, you get transitions from this. So this is R, G, B, V. So remember, this is our H beta. So that one is correct, 4 to 2. So statement A is okay. Then go to the statement B. Energy difference between infinite and 1 denotes the ionization energy. That is also true. You know, during ionization, what happens? We are removing the electron. Right? So if an electron is coming from infinite energy level, that is equivalent to ionization. Because in ionization, what we do, we remove electron, like I said. We get the electron and we push it until it reaches the infinite energy level. That means basically ionizing, removing. So if an electron comes from that energy level to first rank, it is the opposite of ionized electron. Okay, so coming back, it represents ionization. So remember, I gave you a task to find the ionization energy by using the frequency of this line. No, remember that. So anyway, second one is also true. So what about the C? Each line correspond to energy level. No, each line is corresponding to, lines are representing energy differences, delta E. Energy difference is represented. Okay, so it is wrong. Then you can go to the D. It says energy difference between 5 and 3. Energy difference between 5 and 3. Where's 5 and 3? 5 and 3, this one. And is lesser than the difference between 6 and 4. 6 and 4 is this one. So can't see exactly, but according to the diagram I gave you, you can see 5 and 4 will have a larger gap. Let's say this is X and this is Y. X is having a larger gap. So energy of that one will be higher. So telling the energy is less is wrong. Understand? So when you move away from the nucleus, the gap between energy levels decrease rapidly. Okay, decrease rapidly. Therefore, they will come closer together. Right? So anyway, the answer for the question will be answer 1. Okay. Sorry, they are asking the incorrect one. Sorry, I missed. They are asking the incorrect one. So incorrect ones are C and D. So answer 3. Okay. So the last question, the statement or statements false again. False. So the cathode rays are not a type of electromagnetic radiation. So that is wrong. Okay, cathode rays are particles, no? Isn't it? So they are not electromagnetic radiation. You know, in the spectrum we have radio, micro, gamma, visible, UV. Those are the electromagnetic spectrum radiations. Okay, not this cathode rays. So it's wrong. And then the next one, their E over M ratio varies depending on the gas use. That is also wrong. E over M ratio is constant for cathode rays. Okay? So 10th one, A is wrong. Cathode rays are electrons. Cathode rays are electrons. So they are not electromagnetic radiation. They are not photons. You know, electromagnetic radiations are photons. They are made of photons, not electrons, right? And then you can take B. That is also wrong, because E over M ratio for cathode rays constant, remember, because it's always electrons. For anode rays, it is going to be different, constant. Then C, they are generated from cathode and propagate perpendicular to the cathode. That is true. You might remember when we use a concave cathode, all cathode rays will be converging to a single point. That means they are center of curvature, they will all come to that certain point. That means they are released perpendicular to the cathode, no? Okay, so that one is correct anyway. And D, what about D? D is the statement most of you missed, Lamai. Okay, I add this question because of that. They behave as particles in some occasions and they behave as waves in some other circumstances. So why that is wrong? Can anyone give me an idea? Why the last statement is wrong? I took it as wrong. Why? Why it is wrong? So we know that electrons are having particle and wave characters, no? But why this one is wrong? Okay, this is the one, Lamai. Cathode rays are behaving like waves and particles at the same time. Okay, so they are behaving as waves and as particles at the same time. Okay, they are in this question. Look at the way they are telling it. I'll show you again. They are telling that in some occasions it behaves as a particle and in some occasions it behaves as a wave. So like that's how they tell it. So that's wrong, no? Not in some occasions. Always it is behaving like a wave and always it is behaving like a particle. Is that clear now? So that statement is false. Okay, so you can write it in. Okay, Ashima, very good. You got the correct answer. You can say electron behave as wave and particle at the same time. So highlight this sentence also, Lamaya. They are behaving in both ways at the same time. You can't say it is a particle at once and it is wave at once. You can't say like that. It's behaving at the same time in both ways. So then let's complete the review for this also. No, there were some good points. So most of the things we already know, right? And from next week paper, you will see quantum numbers and electronic configuration questions. They will be a little bit interesting than this. We'll see. Let's finish the class for today. Okay, Lamai, then good night. Study well. See you again in our next week paper class.